Now, Euler, in the grand scheme of things, sucks. Here's why. You pick a time step of 10 to the minus 2, and it gives you only accuracy of 10 to the minus 2. Okay? In contrast, let's come over to these schemes over here. Now we get back to this board, because this is where everything matters. Yes?
Constraints on F, I mean, in any physical system, by and large, you don't have to worry about F. It's infinite differentiable and bounded and everything. Or are there cases where you got to worry because F might blow up in some weird way and make your error like blow up in some weird way?
So this is a good time for me to inject some philosophy into this class. Okay, right? For the most part, what we'll assume in most cases, this is an important point. Here, this is differential equation. You can pick crazy F's where all this stuff's going to break down. If you have fairly well-behaved F, what do I mean by fairly well behaved? You know, for my children, fairly well-behaved does not mean that I can differentiate them and they're smooth. Okay, here, that's kind of what this means. Okay, and if you have these so you have discontinuities here, you might have problems where the discontinuity arises. If you have rapid transitions in the solution, problems, your schemes will sometimes break down. In fact, so let me come back to here. This is why we have so many of these. It's because stuff can go wrong. Okay? So mostly what I'll teach to or preach to is the fact that I'm going to give you schemes that sort of generally work in most 99% of the cases. And then, of course, there's always going to be problems that's 1% where problems arise. Now, here's something that's kind of nice about the computer. When there's a problem, the computer tells you. It doesn't say it in words. You look at your solution and you get junk, or it blows up, and you go like, oh, it's trying to tell me something. Okay? Anytime you see a solution blow up or do crazy stuff, and you're like, that doesn't even make any sense at all, it probably means something went wrong. Usually it doesn't hide itself. It announces itself pretty clearly, normally. And then you kind of say, oh, I got a problem. Sometimes you know something about F that you know you're going to get a problem to begin with because F is kind of crazy itself. But for the most part, if you have a fairly nice F, then you have these schemes. Now, the schemes are OD4-5, which is sort of the bread and butter. The 4 and the 5, what do they refer to? Global error, local error. Okay? So, fourth order Runge-Kutta. So what does that fourth mean? It means the error, the global error, is fourth order, but every step you take is actually fifth order accurate. So think about this. You pick a time step of 10 to the minus 2. If you're doing Euler, you get a solution that's accurate to 10 to the minus 2. If you're doing this method, you get a solution that's 10 to the minus 8 accurate. Okay? It's a more sophisticated scheme. But you just dropped the accuracy 6 orders of magnitude. Okay? OD23. Global error. Okay, hold on. Global loco. Okay? Global error, local error. And of course, these schemes were developed specifically with Michael Jordan in mind. That's the part they don't tell you. Okay. 113. This is a predicted. So sometimes some of these schemes break down. OD4-5, you know, again, you're going to be able to do like maybe 90% of the problems out there. Just say, put in OD4-5, go. But there are cases where you have problems which have numerical stiffness, where you have rapid transitions in the solution. It's actually part of the physics of the system. You know, things go along and all of a sudden you get huge changes very rapidly. Well, sometimes your numerical time stepping scheme can't quite change as fast as you want it to. It just ramps up, and OD4-5 completely misses it. Or OD23 doesn't have the tools involved to check out that there's interesting dynamics going on. So you have something like predictor-corrector method, OD113, or these gear methods, OD15S, which is a semi-implicit scheme. But the nice thing, you don't have to write them. They're all there for you. So if you've got kind of crazy behavior, sometimes you kind of go like, all I will do is change 4-5 to 1-5S in my code. And you're putting Smackdown on again, okay? That's the power of MATLAB. You get all this stuff just sitting there for you to use as you need it, okay? So these are the kind of things to think about. And again, like I said, this is an amazing amount of accuracy that's pretty cheap for you to get. Okay. Now, this is an issue of, we're starting to get an idea of accuracy, and you might get the following idea in your head that, oh, you know what, all I got to do is to make this more accurate, just keep dropping that delta t further and further and further down, right? So if my error goes like delta t squared, I pick an error. I want accurate solutions to 10 to the minus 8. Oh, okay, well, let's take delta t to 10 to the minus 4. So every unit you take, by the way, so this costs you. So you take a delta t to 10 to the minus 4, it takes you 1,000 steps to go 1 unit. Now, suppose you have to go 1,000,000 units. Now, normally the computer doesn't complain. Like I said, it loves to iterate. It means that, here's the evolution of MATLAB. It used to be, students come in this class when I started teaching this years ago. They have this idea, I'll write the program, I'll let it run, and then it'll give me results, and then I'll look at them, and it'll be, it's kind of slow. And then you guys, like, I push return and give me something. You guys are like, it should just take 1 second, right? There's something wrong. Okay? So you're used to the computer just kind of flying along. You just say go, and it should just compute this thing out like in a fraction of a second. That's not how it works, really. But it's starting to get that way where people are just expected to go fast. So here, when you start thinking about taking thousands and millions of units at a time, you might not have that kind of time because you got to update your Facebook and stuff. What are you doing waiting around on the computer like that? Okay, so with that, we will introduce techniques by which perhaps you can do more Facebooking. All right. I'm here to help you.